Okay, so let us start. We will review these two chapters, important concept in that, right? So let us start with moving charges and magnetism. Moving charges and magnetism. So in this chapter, first we have to study about Lorentz force. Lorentz force is nothing but the force acting on charged particle which is moving in electric field or magnetic field. Okay. So suppose if there is a charged particle, let us say that this is a charged particle q and it has some velocity v, and in the space around it there is electric field as well as magnetic field. Okay, which direction that we'll see afterwards, but right now you can take in some direction electric field is there and magnetic field, both fields are there. Okay, so let us say that there is some electric field E vector or some magnetic field V vector. So Lorentz force gives the formula how to calculate the net force on this. So the charged particle is under motion, so the charged particle behaves as a magnet. Okay, and because a magnet experience force in magnetic field, so the moving charge also experience force in magnetic field. Anyway, the charge is there and electric field is there, so definitely it will experience electric force also. So the total force on this charged particle, the net force on this charged particle is electric force plus magnetic force. Two forces are going to act. Okay. And you know already the formula for electric force, because in electrostatics you have studied the electric force is equal to charge into electric field. So the electric force which is acting on the charged particle, whether the charged particle is moving or not moving, it will act. Okay. So that's the nature of the electric force. Any charged particle kept in electric field, it will experience that force. So that is given as charge into electric field. And also note that if the charge is positive, then electric force has same direction as that of electric field. What does that mean? That suppose if there is electric field, let us say this is electric field, and let us say that this charge particle is a positive charge particle, then the force will be in the same direction. Electric force is same direction. But suppose if the charge particle is a negative charge particle, then the force is going to be opposite of that. The electric force is going to be opposite because it is a negative charge, right? So this is one thing we have to know. Another thing is about magnetic force. How does magnetic force act? So magnetic force which is fb, magnetic force is given as q v cross b. V cross V. This is the main topic of this chapter, V cross V or magnetic force. Even though when many questions you will find there is no electric force because field is not there. Electric field is not there. Mostly they are focusing on magnetic force. But in case both the fields are there, then both forces you have to take. Right. So here also we need to note that if the charge is positive, if charge is positive, if charge is positive, then the magnetic force becomes parallel means in the same direction to v cross b. So v cross b direction and magnetic force direction will be same if the charge is positive. But if the charge is negative, if the charge is negative, then magnetic force is going to be opposite of v cross b, opposite or anti-parallel or opposite. So v cross b is nothing but cross product of two vectors which we need to calculate according to right hand thumb rule. So that we will also discuss little bit how to calculate cross product. But whatever that cross product direction will come, that direction and magnetic force direction will be opposite if the charge is negative, right? So this is what we need to see. It's a very important thing because based on this force, many calculations are there. Okay. So that's the first thing. So we can also substitute now. Let us substitute the total force acting on the charged particle. So if I substitute this magnetic force and electric force in this formula, so this is the total force acting on that. So electric force is Q E vector and this is Q V cross B vector. Now we can take Q common. So if you take Q common, this become E vector plus V cross B vector. So that's the total force acting on the moving charge particle, right, in a magnetic field as well as electric field. So we will be focusing more into magnetic force in this chapter. So let us start magnetic force. How to calculate magnetic force? What are the different cases that can happen? Like charge particle can move parallel or anti-parallel to magnetic field. It can move perpendicular to magnetic field. It can move in any different direction. All that cases we have to first study. Okay, I think cyclotron is there also, maybe, right? Cyclotron topic is also there, but in NEET I think it is not there. In your board exam it may be there. Okay, we'll see that. In NCERT it is given, right? Cyclotron is given. Did you see that? Cyclotron. Yeah. Okay, done. So that's what is Lorentz force. Now let us focus on magnetic force only. So magnetic force on moving charge. Magnetic force on moving charges due to magnetic field. Due to magnetic field. So let us start one by one understanding. Force formula already we know. Let us write this again. This magnetic force is Q V cross B. Cross product it is. Okay, so let us start first case. If velocity factor is parallel to magnetic field or velocity factor is anti-parallel or opposite to magnetic field. So if parallel means the angle between velocity, this is, let us say, velocity vector, and this is the charge particle. Charge is q, mass is m, and let us say that there exists a magnetic field which is parallel. Okay. So that's the case. So here you have to take the angle between them as 0 degree. And if this charge particle, if the charge particle of q and m is moving with a velocity v factor and the magnetic field is opposite, it is anti-parallel. In that case, the angle between the velocity and magnetic field becomes 180 degree because it is exactly opposite. Right. So in both the cases, if you see the formula for, let us write the magnitude. So magnitude of this force is given as Q. V cross B means VB sine theta. Okay. So that's the formula for magnitude of magnetic force, QVB sine theta. So it depends on the angle between velocity and the magnetic field. Theta is the angle between velocity and magnetic field, and here theta is 0 and here theta is 180 degree. Note that in both cases sine becomes 0 because sine 0 is 0 and sine 180 degree is also 0. So that means in both these cases force is going to be 0. That means the magnetic force is going to be 0 here also the magnetic force is going to be 0. That means if a charged particle is moving in such a way that the magnetic field and velocity are parallel or anti-parallel or in general parallel, then in that case it is going to be 0 force, magnetic force will be 0. Okay? That's the first point we have to note. Right, that's the first case. Now second case, now we know that this magnetic force depend on sine theta, right? So if you want maximum force, then theta should be 90 degree, because sine 90 is maximum, right? So if you want maximum force, then we can take a special case where the force is maximum, for that angle is 90 degree. Okay, so if theta is 90 degree, force will be, magnetic force will be maximum, and that force formula will be QVB sine 90 degree, which is 1. So that's what it will become, QVB. Okay, this case we have to little bit in detail, we have to study that. So when the maximum magnetic force is acting, how can we understand the force and what will be the trajectory? Here note that in this case, because magnetic force is 0, the particle will continue in the straight line. Okay, so here suppose particle is moving, particle will continue its motion in this straight line. In this straight line it will continue. Here also, in this case also, it will continue. Why? Because there is no force, because the force is not there, so acceleration is not there. Acceleration is not there means velocity is constant, so whatever velocity it is, it will maintain constant velocity. Sometimes they will ask in the question, when is velocity constant? So if magnetic force is there, only magnetic field is there, then magnetic force must be 0, then only velocity is constant. So force can be 0 only in these two, this case means parallel or anti-parallel. Okay. Okay, other case, let us take this case. So they can ask trajectory. So trajectory means particle will move in a straight line. Particle moves in a straight line, in a straight line in the previous case. Okay, but now when we see the maximum force acting, so let us try to understand what will happen. Okay, so for this we need to understand what is the V cross V formula. Magnetic force is Q V cross V. V cross V. Okay. Anyway, this will be also getting recorded. You can definitely watch this. This will be a review of the chapter. But previously, when we started, we had more detailed of these lectures and problem solving. Those videos also I will be sharing with you the link of that, right? YouTube videos. So you can definitely watch them if you want to go more detail for NEET. Okay. Right now for your periodic test you are focusing, so we'll focus like that. So QV cross V. Now let us take magnetic field. So here we should be very clear about the direction. Very important thing is the cross product direction. Many students get confused what is cross product and how to calculate that. Let's try to understand this. First of all, direction. So suppose if I take this as x axis and this as y axis. So z axis means it is coming out. So out means what? Out means coming out like this way. But we cannot represent them in 2D because it's a 3 dimension. So we show that line z axis like this. So when we show z axis like this means it is out of the plane. Z axis is coming out of the plane. Okay. So minus z axis is going inside then. So negative z axis will be going inside. Okay. And negative x axis will be coming this side. This will be negative x-axis in this plane. Negative y-axis is going downward. Negative y-axis, this is the origin. Now let us take a case that a charged particle Q, assume that it is a positive charge, okay, and it is moving along x-axis. So velocity is along x-axis. So if I represent the velocity vector of this charged particle, so the velocity is along x-axis. Let us say this is v vector. Okay, velocity vector is along x-axis. Okay, and charge is positive. Magnetic field is going inside. So inside means the magnetic field is along negative z axis. So negative z axis is the direction of magnetic field. But in a plane we can represent going inside and coming out as dot and cross. So we can represent cross, cross, cross. So cross, cross represent here magnetic field lines. Cross, cross, cross. So cross, cross means it is going inside. That means it is going in the negative z direction. Okay. So magnetic field is along negative z direction means unit vector will be minus k cap. You know that, right? I cap is along x-axis positive, minus I cap is negative x-axis, j cap is positive y-axis, minus j cap is negative y-axis, k cap is z-axis, positive z-axis, minus k cap is negative z-axis. Okay, so if you have any time if you have confusion, you can write this with vector. So let us write b vector as b minus k cap minus b k cap. Minus b k cap means b is the magnitude and minus k cap is the direction of the magnetic field. Similarly, if you want velocity vector, you can write as vector. So this magnitude is v and it is going along x-axis, so I cap. So this is velocity vector and this is magnetic field vector. Okay. Now what is cross product means? Very basic, you know, cross product. I think all of you know that cross product. I cross j, j cross k, very easy thing you should know. I j k, let me write it I j k. So if I take I cross j, I cross j, I cross j, if I take, so I cross j gives k cap. Similarly, if I take j cross k, j cross k, j cross k gives I cap. K cross I gives j. Cyclic order. K cross I gives j cap. Right. So if you are going in anti-clockwise direction, this is called cyclic order. I cross j will give k, j cross k will give I, k cross I will give j. But if you go in opposite direction, right, you will get negative. For example, suppose if I go clockwise, let us say like this way, then in that case, j cross I will give minus k. Okay. Similarly, if I go like this, I cross k will give minus j. I cross k will give minus j. Similarly, this way, k cross j, k cross j will give minus I. Okay. So this is very basic of cross product unit vectors. If you take cross product of two unit vector, you will get the third unit vector, and this is a cyclic order, right? Cyclic order means if you go anti-clockwise, you will get everything positive. If you go clockwise, you will get negative values. Okay, this is cross product. So sometimes this cross product using this approach will be very easy to calculate. Okay, if you try to understand, do this cross product. Let us try to do cross product. So magnetic force I want to calculate, which is q v cross b. Okay, let us do that. So q v vector is v I cap cross v I cap cross b vector. B vector is minus b k cap. Minus vk. So minus I will take out. Let us take minus and the magnitude also take out. So minus q v b is coming, and then cross I vector cross k vector you are getting. I cross k you are getting, right? This minus has come here. Q v b are magnitude come out. Then I cross k. Now tell me here I cross k is what? Check out. I cross k means this way. I cross k clockwise you are going, so you will get minus j, right? So that you get as minus j. So minus q v b, this we are getting as minus k. So from here, when you simplify, minus minus will become plus QVB K cap. This is the magnetic force you are getting. So the magnitude of this magnetic force is QVB, and the K cap shows the direction. K cap means which direction? K cap means positive, right? K cap, sorry, did I make mistake? I cross K? I think I made mistake. I minus J, minus J. Minus J it is. Sorry, I did mistake here. Minus J it is, right? So it is minus J, minus plus, so it is J cap. It is J cap. Okay, correct. So the magnetic force is acting in J cap means y direction, right? So from here you can understand the magnetic force is going to act in this direction, upward direction, assuming the charge is positive. So if the charge is positive, it is magnetic force on this when the charge particle is at origin. Okay, when the charge particle is at origin, the magnetic force is acting along y direction. Okay, now the same thing we can understand by right hand thumb rule. Let us understand right hand thumb rule. But this idea is an important idea. Anytime confusion happens, we can calculate that. Let's understand right hand thumb rule. So this is x-axis, y-axis, z-axis, and this is negative z-axis minus z-axis. Okay, so right hand thumb rule says that we have to curl our fingers. So this is the direction of velocity vector, and this is the direction of magnetic field, which is inside. Magnetic field, which is inside. Now let us take V cross B. I will draw a rough diagram to explain V cross B direction. So right hand thumb rule, you curl your fingers in the direction of V to B. Okay, try to curl V cross B. So V cross B means V is going along the x-axis. So your all the fingers except the thumb, right? Except the thumb, all the fingers are going along x-axis, and magnetic field is going inside. B vector is inside. So now you turn your fingers from V to B. That means you have to rotate the fingers, right? So as you rotate your fingers from x-axis to negative z-axis, this is how your finger will rotate, and the thumb is going to point in the upward direction. So this upward direction, which is the direction of the thumb, is giving the direction of magnetic force, assuming the charged particle is positive. Here we have assumed this charged particle is positive. But if the charged particle is negative, then V cross B direction is upward. It has to act downward. Yes, clear? All of you clear? Yes, Monish, Sam, clear? Okay. So that's the direction. Once it is over, then now you have to focus. Now this is the magnitude. We have seen that this is the magnitude of force, but direction, right now the charged particle is here. So as the charged particle is here, the force is acting in this direction. Now let us see this diagram. It will be more clear. Magnetic field I am drawing as cross 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 cross. Everywhere magnetic field is there, cross cross. Okay. Now suppose the charged particle is right now moving like this way. Charged particle is q, mass is m, charge is q, mass is m, and the velocity is in this way. Velocity is this way. So V cross B direction has given the direction of magnetic force upward. Magnetic force upward, and note that this magnetic force q V cross B is always perpendicular to velocity as well as magnetic field, because this cross product q V cross B, this is the nature of the cross product, that magnetic force is always going to be perpendicular to velocity, and magnetic force is always perpendicular to magnetic field. Okay, because the cross product is perpendicular to the plane of that vector. So this magnetic force is perpendicular to the plane of velocity vector and magnetic field vector. Okay, and Because this is always going to be perpendicular like this. Suppose the charged particle moves like this way. Let us say some path is there. Let us say some path will be there, because right now charged particle is experiencing force like this. Now let us say charged particle comes here. So velocity is always in the direction of path, in the direction of motion. This is now the velocity. Note that again the magnetic force which is going to act has to be perpendicular like this. So magnetic force is going to be always perpendicular to velocity and magnetic field. So what is that kind of motion in which the charged particle is moving in such a way that force is always perpendicular to velocity? And note that speed is not going to change because force is not acting along velocity. Because force is acting perpendicular, so speed cannot change. Direction will only change. Okay. So, what kind of motion it is? That is what we have to understand. What type of motion it will be? Think about it. What kind of motion it will be in which the speed is not changing, speed is same, and force is perpendicular to velocity. What kind of motion it is? Force is perpendicular to velocity and speed does not change. So that is definitely a circular motion, and that too uniform circular motion. So this is going to be a uniform circular motion. So what happens in uniform circular motion? In uniform circular motion, speed never changes, speed remains same, but velocity keep on changing. Velocity means direction changes. Why? Because force is always toward the center, that is called centripetal force, right? Yes, centripetal force, you know that. But there can be a circular motion in which the speed can also change. That is a different type of circular motion. That is called non-uniform circular motion, right? But here speed is not changing. So this is a uniform circular motion. Okay, and in uniform circular motion, the only force is centripetal force. That means this force, magnetic force, is the centripetal force, or magnetic force is acting like a centripetal force. Okay, so we can now conclude that magnetic force is like a centripetal force. So magnetic force is like a centripetal, and centripetal force formula is mv square by radius, right? Suppose the radius of the circle is r. This circle has a radius r. So mv square by r. Now we can equate. So magnetic force is maximum. We know that. So magnetic force is qvb, and this is mv square by radius. So from here we can simplify this equation and we can cancel out. V will get cancelled out. So from here you will be able to find the radius of this circular motion. Radius is mv by qb. And this mv is nothing but momentum, magnitude of momentum. Okay, momentum is a vector, but this is magnitude of momentum. So momentum divided by qb, or mv by qb, that's the radius of the circular motion, uniform circular motion. So if a charged particle is projected perpendicular to a uniform magnetic field, then the charged particle will go in a uniform circular motion. The radius of that circle is mv by qb, or momentum by qb. Clear? Okay, and here you need to note one important thing, that the ratio of charge to mass q by m is called alpha, and this alpha is called specific charge. Specific charge. So sometimes the formula for radius can also be written in terms of charge to mass. So v by alpha b. It can also be written in terms of specific charge. So if you consider a specific charge to mass ratio, if you take electron proton, so alpha of electron and alpha of proton, if you compare, proton has little bit larger mass. Okay, little bit larger mass as compared to, not little bit, more, much more, I think, almost nearly 10 lakh or something. So mass of proton is quite large, okay, and mass of electron is quite less. Charges are same. So if this is small, right, so that is going to be large. So alpha for electron is larger than alpha for proton. That we should note. Okay. And if you also consider other particles like alpha particles, then alpha particles you can see the charge. Charge is 4 times of electronic charge. Mass, sorry, charge is 2 electronic charge. Mass is 4, right? Mass is 4. So that also you can compare if alpha particles are also given. You can compare alpha particles and this. So here charge will be 2 times, mass will be 4 times, so 1 by 2 times. So alpha particle, sorry, this specific charge of electron is greater than that of, you know, alpha particle, alpha particle, alpha particle, and this is greater than proton, proton. Okay, P. So that also we should know. And suppose if everything is same speed and same magnetic field, then according to this, no, radius can be different. Okay. So now suppose if I consider alpha particle and proton, electron, if I consider that and keep the speed same, suppose if speed and magnetic field are same, so we can say that the radius of the circular motion is inversely proportional to this alpha. Proportional, okay, this sign is proportional to this is alpha. And alpha, we know that alpha whichever is large. So if I have to compare radius of electron, if I have to compare, so because this is going to be larger, so electron radius will be smallest. So radius of electron is going to be smallest than radius of alpha particle, then it is going to be smallest than radius of the proton. So sometimes questions comes based on this. Remember the condition is important. The condition is that the speed and magnetic field are same. Speed and magnetic fields are same. Then we can apply this. Clear? Okay. But if they say the kinetic energies are same or accelerating voltages are same, then how do we compare that? Then we need to write this formula in terms of that. So then you write this formula again. Radius is mv by qb, mv by qb, and let us say we can write this as momentum charge into b. Momentum can be written as root under 2 times mass into kinetic energy, mass into kinetic energy divided by charge into b. Okay. Now kinetic energy, if the kinetic energies are same, then also we can compare, okay. But suppose they say that accelerating voltages are same, then this kinetic energy can also be written as charge into accelerating voltage delta V. Delta V, charge into voltage, voltage difference, that is the kinetic energy, because that's the formula for work done. Okay. So from here, the formula for radius can also be written in terms of that. Radius can be written as root under 2 times mass. This charge will go inside, so q b square, okay, then delta v. Like this also we can write. If you want to write in terms of alpha, so root under 2 delta v, charge is to mass is alpha, so alpha b square. Like this also we can write. Okay. So sometimes they say that the charged particle is accelerated, so voltage difference we have to also consider. Clear? Any doubts? Okay, so these are some of the important formulas of radius. Okay, then because the charged particle is undergoing a circular motion, we can calculate something more. What is that? We can calculate the time period of that circular motion, because charge particle is going in this circle. So suppose the charge particle is q and mass is m, it is going in that circle. So if I want to calculate time period, so time period is 2 pi by omega, 2 pi by omega. Or you may also simply write as distance by speed. So in one circle distance is 2 pi r, 2 pi r divided by speed. That also you can calculate, 2 pi r by speed. Now radius formula we know, let us substitute. So radius is mv by qd. So divided by v, vv get cancelled. So you get 2 pi m by qb. Now this is very important to note that the time period which is 2 pi m by qb, or you can also calculate angular velocity omega, which is 2 pi by time period, which will come as qb by m. So angular speed means what is the rotational speed of this charged particle around the center. Omega is angular velocity or angular speed. So this time period or this angular speed does not depend on the linear speed. So whether it is going with high speed or whether it is going with small speed, the time period for one circular motion is going to be same, because time period only depend on mass and charge. So you can also say that time period is 2 pi by alpha b, because charge to mass is alpha. So this alpha time is very important, because it is coming in almost all the formulas, charge to mass ratio. Okay. So that's what it is. Okay. Magnetic force and calculation of radius, calculation of time period. Frequency is 1 by t, so you can also calculate frequency if you want. Frequency is 1 by t, so that will become qb by 2 pi m, right? So like that we can calculate. So that's all. This is case. Then last case, which is the most important case, is if the charged particle is thrown without 0 degree, 180 or 90 degrees. The third case is the most general case. Okay, general case. So if the charged particle q mass m is thrown at the velocity v, okay, and this velocity is making some angle alpha with, or some angle theta with magnetic field. So now this theta can be anything, any values of angle except 0 degree, 180 and 90, because those cases we already have taken. So this is some angle which is neither 0 nor 180 nor 90 degrees, some other angle. So in this case what is going to happen? Note that velocity and magnetic field is in this vertical plane. Okay, this is the vertical plane of the blackboard. So that's the vertical plane. Okay. Now V cross B, if you apply right hand thumb rule, so this is V and this is B, so you have to turn the finger from V to B. So if you turn from V to B, thumb is going inside. Thumb is going inside means the force is going inside, and that force means the center of the circle must be inside this. Okay, center must be inside. Okay, but how to understand this, or how to do calculation for this, we can break it into two parts. One velocity resolution will be along magnetic field, which is V parallel. V parallel is nothing but V cos theta, and another is V perpendicular, which is V sin theta. So now we can easily study this type of motion, because V parallel means it is parallel to magnetic field. So that means this velocity will not get affected due to magnetic force, because magnetic force does not affect this velocity. We have seen previous case, if velocity is parallel to magnetic field, that velocity will not change, it will continue in a straight line. So due to this velocity, it will continue in the straight line. But we have also got another velocity which is perpendicular to magnetic field. So due to this velocity, it will experience centripetal force, right? And if you see V cross V, it is inside. So center is inside this circle, inside this plane, and it is also going to move forward. So now what is going to happen is this is going to experience a force like this. It will be going like this, it will come back, again it will go like this, again come back, again it will go, again come back like this. So the plane of this circle, very important to understand, the plane of this circle is perpendicular to this plane like this way. Okay, so perpendicular means how it will look like. Just let me show. It is like this way. Okay, it is like this. This plane is the plane in which we have thrown it, right? But this plane we are talking about, the circle is in this plane. So suppose you have projected this right now, so circle will be going like in this plane. In this plane circle is happening. So center will be inside. Suppose this, now if I show like this, you circle is like this, so center will be exactly in between, right? So that center which is in between this, it will go inside now. Okay, that is what we have to imagine. It is like a more about imagination also, because three-dimensional diagram it will be. Okay, so the particle will go inside, and note that again it will be coming back here, again it is going, again coming back here. So it is going to hit this x-axis because it was projected from x-axis. It is going to hit the x-axis again and again, again and again it will hit that. So the time when it will hit that means it will be completing one circular motion in that plane, right? So one circular motion it will complete. So this distance which is moving forward in every circular motion in this plane, this distance is called pitch. Okay, this distance is called pitch. And this pitch is same because the speeds are same. So that's the pitch. So pitch, how do you write pitch? So pitch we can calculate as speed in this direction is v parallel, and how much time it takes for one circle, that is t. Okay, and time for one circular motion can be calculated using this formula. So time period is 2 pi m by qb, 2 pi m by, so we can substitute this time period here and we can calculate this pitch. Okay, so this pitch can be calculated as 2 pi m by qb, this time multiply with v parallel. V parallel is nothing but v cos theta, so 2 pi m into v cos theta divided by qb. That is the pitch. Pitch is the forward distance moved by the charged particle after completing one circular motion. Okay, that's what it is. And here what is the radius of this circle? Radius formula will be same. Radius is mv by qb, but remember this v will become v perpendicular because v perpendicular to the magnetic field is this v perpendicular, which is v sin theta. So we can write mv sin theta divided by qb. In terms of alpha also we can write it. So that's the radius. So this what type of path it is? It is called helical path, uniform helix. Okay, this is called uniform helix, uniform helical path or uniform helix. Uniform helix means what? Uniform helix means the pitch is equal. It is not like, non-uniform. Non-uniform pitch will be like this way. Okay, so first it makes circle like this, next again it is like this, next again like this. So this distances after one circle is increasing, so such type of motion is a non-uniform helix. That non-uniform helix is also possible if speed increases in this direction, right? That is also possible, but right now in NCRT it is not there. Non-uniform helix is not. Maybe in NEET it can happen, okay, but not in this one. Okay, so that's what it is, radius. So over, so this is all about magnetic force. Okay, now let us understand the deflection formula for deflection. So suppose if you consider magnetic field, so most of the questions will be like this. Okay, perpendicular magnetic field will be there. Let us say that this magnetic field is perpendicular like this. Magnetic field is perpendicular and the charged particle is entering. Magnetic field is only present up to a distance of d. Okay, and a charged particle q and mass m is going to enter with a speed v. So as this charged particle is entering, right, and this charged particle is going to enter inside this, what is going to happen in that? Yes, this is going to experience a magnetic force. So which direction magnetic force? In this direction magnetic force. Assume charged particle is positive, so it will go like this way. Correct? Like this it will go. It will go like this. And suppose it completes up to this much, then let us say that it is not able to complete one full circle, so it will be exiting at this point. At this point it will come out with a velocity v. Remember that speed does not change but direction changes. So where is the center of this circular motion? Center of the circular motion somewhere here it will be. So the thing is that how much this angle is, that is the question. What is this angle? So note that this is d, so this distance is also going to be d, because this is the distance of magnetic field d, and this is the radius. Note that this is the radius. So if you use sine theta from here, sine theta comes as d by r. That's how you can calculate, and radius you know, radius is mv by qb. So this is how we can calculate sine theta, or theta can be calculated from here, right? That's what moving charges magnetism. Mostly questions are this way. What about the magnetic effect chapter? Any doubt in this chapter? Tell. Tell me. Magnetic field due to infinitely long wire carrying current, right? Okay. Okay, let's take that. So suppose if we have a very long wire like this carrying current, very long, okay, and it's very long means very long it is, okay, and I want to calculate magnetic field at some place. Where do we want to calculate? Anywhere here we want to calculate, okay, here, which is at a distance of, let us take this distance as d, or r. Let us take r. No, keep it as d, that is better, because r we will choose as variable. Okay, this is d, perpendicular distance. I want to calculate magnetic field here due to the entire wire, so I am going to use Biot-Savart law. I think you know Biot-Savart law, right? So this is the current, and this length is dl. So this is small length dl. We have to, let's write this as ideal vector. So this is small point that we are taking is on the wire, okay, carrying current. Current is not a factor, but this ideal is just a small point. That is small point act like a factor. Okay. So now due to this distance we need to see. Suppose if I join this, okay, and let's say that this angle is theta, and this distance is very small, d theta, very small angle. So due to this r factor also we should note, this is the r factor. R factor is a factor going from this way, from here to here. This is r factor. Okay. And if I take that this angle is theta, then this angle will become 90 minus theta, because this is 90 degree. This is 90 degree minus theta. See, one shortcut derivation is using Ampere's circular law, but that's quite easy. That is not big thing. But using this Biot-Savart law, that is important, because they can ask in exam using Biot-Savart law. So now let us try to find out magnetic field due to this. So magnetic field using Biot-Savart law, this formula we should know. PV vector is mu naught by 4 pi I dl cross r cap by r square. Okay, what is this formula? Suppose if there is a current carrying wire and let's say that there is a small element carrying current ideal, and at this point, which is at a distance of r vector at an angle of theta, so magnetic field at this point is given by this formula, ideal cross r cap. R cap is a unit vector in this direction. R cap is a unit vector in this direction. Okay, so same way we are taking here ideal cross r. Let us write down this magnetic field, that magnetic field. So what will be that? I will write it here. dB magnitude, let us write. So mu naught by 4 pi, mu naught by 4 pi, ideal, ideal cross, when you take cross means ideal magnitude, ideal r cap magnitude is 1 only, sine of 90 minus theta you have to take, right? Sine of 90 minus theta you have to take, divided by r square. So let us write this. And what will be the direction of this ideal cross r? Means it will be in this direction, cross, right? Ideal cross r means going inside. Okay, so let us try to write this. So dB is equal to how much it is going to be? Let's write. So mu naught by 4 pi ideal, ideal sine 90 minus theta become cos theta by r square. Okay, this is the small magnetic field due to this element. As the element changes, the magnetic field may also change. So we need to integrate this, right? All the note that all the magnetic field is cross means it is very easy to do the integration, right? It's very easy to do integration. So let us try to do that. We need to do integration of this. So integrate this. So that will be the net magnetic field at that place, and note the direction is cross. Okay, we know already the direction is cross. Constant terms you take out. So mu naught by 4 pi comes out. Integration remains. I is also constant current. Current also comes out. Mu naught I by 4 pi cos theta dl by r square. These terms remain, right? And we have to take each element on the wire. Remember this angle is going from we will see afterwards, angle can go from this side to that side, but this end is going at infinity downward, that end is also going infinity down upward. Okay, but we will integrate it. You can take a finite wire also and make it infinite, that is also possible. Let us take that case only, it will be better. So that means you are taking a wire which is finite, okay, at a distance d. Here you want to calculate magnetic field, and let us say when you are joining the ends of the wire like this, these angles are, let us say, alpha, and upward angle is beta. Okay, so this is finite angle, but suppose if this wire become infinity, I think network problem was there. Okay, are you able to understand this? Can you see this? Okay, so what I am saying is, if I take a finite straight wire, so that wire will be making alpha beta, the ends of the wire will make alpha beta with this point. Okay, and if you want to make this infinitely long, then alpha beta will become each 90 degrees, because this point is going down, so this alpha will increase and it will become 90-degree downward, and beta will become 90-degree upward, like that it will become. Okay, so that's the key idea. So let us do this integration here, and note that while you are taking this alpha beta, right, so you need to have a direction of the angle. So this is the horizontal line, and this is downward and this is upward. So you have to take one angle as minus alpha, another angle as plus beta, because these angles are, one is down and up, so you have to take one as minus, another as plus, and even you take minus plus, it doesn't matter, but it has to be opposite. Okay, but if they are in the same direction, then we have to take both as plus alpha plus beta. Okay, or minus alpha minus beta, same sign you have to take if they are in same direction. But here opposite means one is minus, another is plus. So let us do this integration. I am taking this integration from theta 1 to theta 2. Limits are there. But how to do this integration, that is the most important thing, how to do this integration. If you can understand this integration, that means most of the question is over here. Okay, most of the derivation is over. So how to do this integration, this part we have to understand clearly. Okay, so let's note that small element, this dl, I am going to note this small line dl, right? And this is the y and this is the point, right, which we are joining it here like this. So this length is dl and this angle is d theta. Okay, and note that this angle is theta and this distance is d and this is perpendicular. Okay, so here you have to note that this dl is not the arc length, right? So to make the arc length, you have to draw arc length like this. Okay, so this will be radius r, right, and this is the arc length. Okay, so if this is the arc length, if this is the arc length, then note that angle between these two lines is same as angle between their normal. So this is horizontal line, so and this is the vertical line, and this is like the radius and this is like the tangent. So you have to note that this angle is also going to be theta. Very, very important. This dl and this arc length is making the angle theta. Okay, that's a very important thing. If you know this one, then you can resolve this dl in this direction. Dl in this direction becomes dl cos theta. This is what it is, dl cos theta. This side will become dl sin theta, but dl sin theta we do not have to use it. Okay, dl cos theta we have to use. So what is dl cos theta? Dl cos theta is the arc length of this, arc length. So dl cos theta becomes equal to arc length is radius into theta, you know that. So radius into d theta, because this is the angle subtended by this arc length, dl cos theta. So dl cos theta subtends a small angle d theta. So radius into this angle becomes arc length. That's the most important thing. Now I think we can very easily do this calculation. Okay, dl cos theta is r d theta. We can substitute it here also, and also note that in this triangle, the cos theta is base d by r hypotenuse. That is also important. Okay, so now these two things we'll substitute here and we'll calculate magnetic field. So magnetic field, which is mu naught I by 4 pi, let us substitute. So cos theta into dl, if you substitute dl cos theta, it becomes r d theta, and in denominator we have r square, so 1 r got cancelled. So we got mu naught I by 4 pi integration. Now r we will substitute from here. So from here r will become d by cos theta, so substitute. So d theta and 1 by r means it is d by cos theta. So cos theta divided by d will come. Now this integration is very easy. Cos theta integration, we know that. So theta 1 to theta 2 are the limits. Okay. So mu naught I by 4 pi cos by d, d is constant. Cos theta integration is sin theta, it is sin theta, and we have to take from theta 1 to theta 2. Okay. So let us do this integration. So you got finally the magnetic field formula, mu naught I by 4 pi d sin theta 2 minus sin theta 1. This is the final formula, and this formula is for finite wire. What is that finite wire? This is the wire. It's a finite wire, and the ends of this wire is subtending some angle here. Okay, this angle is theta 1, theta 2. Let us say here we have taken alpha, beta. So theta 1 I am taking as minus alpha, theta 2 I am taking as plus beta, because they are opposite. Okay. So now if I substitute, here, what formula will you get? You will get mu naught I by 4 pi d sine of beta and minus sine of theta 1 is sine of minus alpha, which will become minus sine alpha. So minus minus will become plus, and that's the formula for finite. And if you want infinite, for infinite wire, alpha is equal to beta is equal to 90 degrees. Substitute this 90, 90. Sin 91, sin 91, 1 plus 1 will become 2, and that 2 will cancel here denominator 4. So mu naught I by 2 pi d, that is the formula for magnetic field due to infinitely long wire. Clear? This question can come in board for 5 marks. Okay, Biot-Savart law means more application, means 5 marks it will come. But if they ask Ampere circuital law, that can come in 3 marks. Okay. Then anything else? Any other doubts you have, because it's not possible to complete the entire chapter, right? One hour not possible. You can clear your doubts. That's what we can do. Done. Okay. Okay. Then we will see the next class. All the best. Write your exam nicely. Okay. Then we'll see afterwards. Okay. Bye bye then. Hmm?